Okay, so today we're going to talk about independent events. So if you can open up your probability packet, and this is on the top of the page where number 15 and 16 are. All right, now this is how it works. Two events are independent of each other if the probability of one event has no impact on the probability of the other event occurring. Okay, so we have two rules that we use for independence. I'm going to actually start with the second rule right here. It says two events, A and B, are defined as independent if. Now we read this as the probability of A given B is equal to the probability of A. So what that means is if we're given B, okay, if we want to find the probability of A occurring given that B occurs, it's just going to be equal to the probability of A. Because if A and B are independent of each other, it doesn't matter what the probability of B is. If they're independent, the probability of A given some event that has no impact on it is just going to be equal to whatever the probability of A should be. Okay, so this rule, I mean, it's pretty much self-explanatory. All right, now this first rule, this one we use a lot in Algebra 2. I mean, this rule, some people prefer to use this rule over this first rule, but the first rule you're going to see as we go through these, this one we're going to use a lot. All right, this one says two events, A and B, are defined as independent if the probability of A and B is equal to the probability of A times the probability of B. So what that means is they're independent if the probability that they both occur are equal to the product of their individual probabilities. Okay, so now what I'm going to do with you is I'm going to do the even examples on the next few pages. And in each of these examples, we're going to use one of these two rules for independence to help us. All right, so let's take a look at number 16. So I'm doing the even, so we're going to skip over 15. All right, number 16 says, there is an 8% chance that a person picked at random from the adult population is, it should say, a regular smoker of cigarettes. Okay, so I'm going to just stop right here and say the probability that someone is a smoker is 8%. Okay, so that would be 0.08. So I'm just going to write this out. Okay, now as we keep reading, it says, and a 1.8% chance that a person picked has emphysema. So let's say the probability of emphysema, so we'll use an E for emphysema, is 1.8%, so 0.018. Here, remember, we have to move the decimal place back 2 spaces to the left to get these numbers. All right, it says if the percent of the adult population that are both regular smokers and suffer from emphysema is 0.144%. So let me write this out. So they're saying the probability that the person is a smoker and, remember this is our symbol for and, has emphysema is 0.144%. So if I move the decimal place back twice, that'll be 0.0144, is being a smoker independent from having emphysema. All right, now, let me just go back up to our formulas up here. And I want to point out, see how we see the and symbol right here? Because they give us the and, we're going to use this formula with the and in it. So we know that two events are independent if the probability of A and B equals the probability of A times the probability of B. So I'm going to use this formula, but instead of using A and B, let's use S and E, okay? So let's write this out. The two events are independent, and you guys should be writing all this, independent if the probability of S and E, so remember we're using S and E instead of A and B, equals the product of their individual probabilities. So the probability of S times the probability of E. Okay, so I'm just going to take the numbers and I'm just going to plug them right in. So we know the probability of S and E is 0.0144. Oh, did anyone pick up on that mistake I made? If you move this back twice, it's 0.00144. Okay. And then I don't know if these are equal, so I'm going to put a question mark on top of this because we don't know right now. Now the probability of S is 0.08. So let's replace that with 0.08. And then times, I'm just going to put these in parentheses to show we're multiplying. the probability of E is 0.018. Okay, so let me bring down the 0.00144. And then I'm just going to multiply these together. And when you do, look at that, you actually get the same exact thing, 0.00144. So this checks out. So since this equation holds true, we can say our events are independent. So now we just want to write out a statement. So we could say, yes, these events are independent because, and I'm just going to state the rule, the probability of S and E equals the probability of S times the probability of E. So, I mean, with these questions, as long as you know the formula, they're actually, like, pretty easy. Okay, so again, we're skipping to the evens, so you can jump ahead to the next page and look down at number 18. All right, so when you look at number 18, it says, complete the following hypothetical 1,000 table. Okay, so what this means is, I mean, this table is not complete, but they want us to fill in the missing numbers. Now, we know that this is our total. So if this is 1,000 and this is 800, you could say 1,000 minus 800 would be 200. So in this box, we have to have 200. Okay, and then 1,000 minus 600 would be 400. So in this box, we'll have a 400. Okay, you're just going to make sure everything adds up. Okay, it doesn't really matter like where you start, but if we look at this row right here, 200 minus 50 would be 150. So I could put a 150 here. All right, I guess next I'll just do 400 minus 150 is 250. So this would have to be 250. And then 600 minus 50 is 550. So this will be 550. And it's a good idea just to make sure everything checks out. Make sure these two numbers add to 800. Make sure these two numbers add to 200. And just, you know, make sure as you add down, everything works out as well. Okay, so we completed this. Now it says, are the events participates in extracurricular activities? So I'm going to make this P for participates. And know what I want to do after high school. So here's know what I want to do after high school. I guess I'll make that a K for no. Independent or not independent. Now, we can use either one of the two formulas from the previous page. I'm going to stick with the formula that we just used because that formula is pretty easy. I find, you know, most people choose that one over the two. So we know that the two events are independent if, and you can copy that formula off the previous page. I'm just going to use, instead of A and B, I'm just going to use P and K. So they're independent if the probability of P and K equals the probability of P times the probability of K. Okay, so now we just have to look at our table and just figure out what to plug in where. So now the probability of P and K. So P and K, participates in extracurricular activities and knowing what I want to do after high school. Well, there's 550 people that fit into both of these categories, right? This 550 is in this column and this row. Now, this is 550 out of the total number of people. Okay, you're always going to use the total for your denominator unless you're using a given, but we're not using a given here. So the probability of P and K is the 550 out of the total 1,000 people. Now I'm going to put a question mark on top of that equal sign because we don't know if this is true. All right, now let's think about it. Over here, the probability of P, the probability of participating in an extracurricular activity. Well, there's a total of 600 people that participate in extracurricular activities out of the total 1,000 people. So we're going to write that as 600 over 1,000. Okay, and then we're going to multiply that by the probability of K, so the probability of knowing what you want to do after high school. So there, if you look at the total of this row, there's 800 people that know what they want to do after high school out of the 1,000 that are represented here. All right, so now let's just see if these two sides of the equation are equal to each other. All right, so, 550 over 1,000, if you want to change that to a decimal, that would just be 0.55. We want to know, is that equal to? Well, if you were to multiply these out, 0.6 times 0.8, or you can plug them in your calculator to give you 0.48. Okay, these two are not equal. Okay, 0.55 is not equal to 0.48. So what we can say is that no, they are not independent. So they are not independent. And I'm just going to say because, and I'm going to state the rule, and I'm just going to put a slash to the equal sign. So because the probability of P and K does not equal the probability of P times the probability of K. And by the way, if you wanted to use that other rule on the front of the page, you could just show that the probability of P given K does not wind up equaling the probability of P. So if you want to use a second rule, you'll also be able to see that these two events are not independent. Okay, so if you keep flipping, right, we're doing the even. So if we go on the next page, let's take a look at number 20. Now this one doesn't fill in the table for us. I mean, if you want to look ahead and see what you can fill in before you even read, you could say, all right, 1,000 minus 700 is 300. So that would go here. And 1,000 minus 600 is 400. So that'll go here. Now, unfortunately, we don't know any of these numbers. So we can't just like guess at one and fill in the others accordingly. So let's see what this question's asking. It says, complete the table below in a way that would indicate the two events, uses a computer. So I'll just do C for computer. And is taking a math class. So let's use M for math. Are independent. So they want us to fill in this table in a way that would show that this and this are independent. All right, so this could be a little tricky. Well, let's think about our rule. Let's use the same rule we've been using. We know that the two events are independent if, and let's just state the rule, the probability of M and C equals the probability of M times the probability of C. Okay, so we know these two events are independent if this rule sticks. Now, the probability of M and C would be this number over 1,000. So we don't know this number. Do we want to just call that X for right now? Let's call this X, okay? That's what we're solving for, I'm assuming. So this would be the and over the total. So here, the probability of M and C would be whatever goes in this box over the total, so X over 1,000. All right, let's hope we know everything else because we got to solve for that X. Okay, now the probability of M. So here's M. Well, we know there's a total of 700 people who are in a math class out of the 1,000. So we could just write this as 700 over 1,000. So that we do know. Okay, and then times the probability that someone uses a computer at least 3 times a week is 600, right? 600 total out of the 1,000 total. So 600 people use a computer out of the 1,000 people here. All right, awesome. So all we have to do is just solve for X, so this shouldn't be too bad. All right, so let me bring down the X over 1,000. And if we multiply this fraction by this fraction, you would get, so this is equal to 0.7, this is equal to 0.6. If you multiply these out, it gives you 0.42. All right, so now if we want to get this X by itself, since X is being divided by 1,000, the opposite of division is multiplication. If we want to get rid of this 1,000 in the denominator of the fraction, we can just multiply by 1,000. Now, if we multiply the left-hand side of the equation by 1,000, we have to do that on the right side as well. So on the left, this 1,000 on top cancels with the 1,000 on bottom, so we can bring down the x. And then 0.42 times 1,000 is 420. So this 420 is what's going to have to go in this box with the x. So let's erase that x. Okay, we now know what x is. X is equal to 420. And now that we know this, we can fill in all of the other boxes. All right, so let's start with this one. 600 minus 420 is 180. So we could put 180 right here. Okay, and then 700 minus 420 would be 280. So we could put the 280 right here. And then 300 minus 180 is 120. So we could put 120 right here. And I always like to double check and make sure everything checks out. 420 plus 280 is 700. 180 plus 120 is 300. Good. And then as you count your way down, work your way down, 420 plus 180 is 600. And 280 plus 120 is 400. So this all works out. So here we go. We're done. Well, with number 20. Okay, so in number 22, they give us some information here and says determine whether gender and passing the test are independent. Okay, so this column represents pass the test, so I'm going to call that P. And then when it says gender, I mean, you could pick either one. You could pick males or females. Okay, you'll get the same answer either way. So I'm going to pick males. But you may want to make a note that in order to determine this, you can pick either gender. Okay, so if they're not specific with gender, you can pick either gender, male or female. Okay, that's up to you. So I decided to pick male. So let's just use our rule for independence. So we know that gender and passing a test are independent if the probability of, I'm going to use M for male, and P for passing the test is equal to the probability of male times the probability of passing. All right, so let's look at our table. So if we want the probability of being a male and passing the test, well, this right here, there's 78 males who passed the test. So that would be 78 out of. Now, what's a good idea here is I should have from the beginning added up all of these columns and rows just to total everything out. So let me do that. 78 plus 26 is 104. 69 plus 23 is 92. So if we add those together, that gives you what? 196 total. Okay, now let's add our columns. So 78 plus 69 would be 147. And then 26 plus 23 would be 49. And just to make sure this all checks out, if I were to add up 147 and 49, that does give me 196. Okay, so let's go back to this. The probability of male and passing. So we said there were 78 males who passed out of the total 196 people. Okay, now above this equal sign, I'm going to put a question mark because we don't know if this is equal or not. Now the probability of male, let's see, males, there was a total of 104 males out of the 196 people that were surveyed. So 104 over 196, and then times the probability of passing. So altogether, there were 147 students who passed out of the 196 students. So 147 out of 196. Okay, so let's see. If I were to, let's say, if I plug in my calculator, 78 divided by 196, it gives me a decimal. If I hit math, enter, enter, it actually does change to a fraction in simplest form, which gives me 39 over 98. Okay, so basically we were just dividing top and bottom of this by 2. And then let's bring down the equal sign. We don't know if we're going to cross it off yet. If you were to multiply these two out in your calculator and then hit math, enter, enter, look at that. It actually does give you 39 out of 98. So this actually checks out. So what we can say is that gender and passing the test are independent because this rule works. Okay, so you're just going to want to write this out. Okay, so gender and passing the test are independent because this rule right here, the probability of male and passing is equal to the probability of male times the probability of passing. Okay, so let's keep going with the even. So if you turn to the next page, number 24, and we're going to stop, 26 will be the last one we're going to do together. Okay, so it says the following table describes the departure of buses out of a bus station for this past summer. All right, so it looks like here it's giving us the months, and it's saying departed on time or delayed. Okay, part A, determine the probability that the bus is on time. All right, so here are all the buses that departed on time. So it was a total of 112 of them, and that's going to be over the total number of buses that departed throughout the summer. So it would be 112 out of 200. Now, if you want to simplify that, you can, but with probability, it's not necessary to simplify. Because sometimes you want to see the total. Sometimes you want to say, look, there was a total of this many that departed out of the total number of buses. Okay, now, the next part says, determine the probability that the bus is delayed given that it occurred in July. So let's see, here's our column for delayed. I'll put a D for delayed and a J for July. Okay, so we're given that it occurred in July. So if we're given that it occurred in July, we're only looking at this given row. All right, so the total in that row is 79. Now, so that's going to be the denominator of our fraction. Okay, now the numerator would be the number of buses that are delayed within that row of July. So the number of buses that are delayed within this row are 35. So the answer here would be 35 out of 79. And this one actually doesn't simplify. If you want to think about your formula here, we know that the probability of being delayed given July is equal to delayed and July over how many buses are delayed. So here, delayed and July would be 35, so that's our numerator. And then how many buses were there total in July? 79. So you could think about the formula too if you want. Okay, and then finally part C are being delayed. So I guess we'll use a D again for delayed. And the month of June, independent events. All right, so this time, you know what I'm going to do? I'm going to erase my J right here, and I'm going to put the J for June. All right, so we know that our events are independent if, and let's state the rule, the probability of being delayed and June is equal to the probability of being delayed times the probability of June. All right, so let's look at this, the probability of delayed and June. All right, let me do this too. Let me erase this because we're no longer using that row. We're actually using June, this row, and delayed, this column. So the probability of delayed and June would be where June and delayed intersect, which would be 23 out of the total 200. So 23 out of 200. Okay, and let me put a question mark on top of this equal sign because we don't know if it's true. Now the probability of being delayed, well, there was a total of 88 buses that were delayed out of the 200, so 88 out of 200. And then times the probability of it being June, there were 63 total buses in June out of the 200 buses. Okay, so now let's see. On the left-hand side of the equation, 23 over 200 doesn't simplify. I'm just going to bring that down. And then if I were to multiply these together and I guess hit math, enter, enter, I would get 693 over 5,000. Now these are not equal to each other because if they are, this fraction would simplify to give us this. If it's easier for you to see, you can change this to a decimal and then change this to a decimal, and you will see that they're not equal. Okay, so now we can just state our rule. They are not independent because the probability of D and J doesn't equal the probability of D times the probability of J. Okay, so we're just going to state this rule. Just put it into words. Okay, and then you can turn to number 26, and that's the last one that we're going to do together today. Okay, so number 26, I'm just looking at it. I think it's actually the easiest one out of the ones we have to do today. It says that given that events A and B are independent, they give us the probability of A, they give us the probability of B, and they want us to determine the probability of A given B. Now let's think about this. If we know that they're independent, what that means is that the probability, my pen's not really working well here, of A and B is equal to the probability of A times the probability of B. Okay, so this is the rule we're going to be using. Now, they tell us that the probability of A is 0.85, so I'm going to substitute that in here. And they tell us that the probability of B is 0.2, so I'm going to replace the probability of B with 0.2. And they want us to find the probability of A and B, so they want us to find this. All right, so the probability of A and B is just going to be equal to whatever the product of these two numbers are. So if you multiply 0.85 times 0.2, that'll give you 0.17. So that's what the probability of A and B is equal to. Now, I'm just looking at the examples we did today. In the beginning, we did say there's two formulas we can use for independence. We really, on all the examples we did today, we only used this first formula, but you will see that, tomorrow in class or the next day, we will be also using the other formula for independence.